Well, thank you everyone for coming to the Zoom APS March meeting. I'm presenting this talk on behalf of my former student and postdoc, Zara, who has actually now gone to work with Mark Peterson. Zara told me she's very busy. Mark must be keeping her very busy, so she couldn't give this talk. I'll talk here about the effect of substrate on the characteristics of Mn3 dimer, something that I will talk more about in the next talk. And this work is actually done, it's funded by the DOE EFRC that is located at University of Florida, of which we are a part. To begin with, let me mention here this molecule that was synthesized by George Christou at University of Florida and also characterized by Steve Hill and other co-workers. So basically what they find in this single molecule magnet is that this is, first of all, is manganese 3, so 3 manganese atoms, as you see over here. And essentially, they were able to create a dimer out of this. And of course, it depends on the ligands that they use. And depending on the ligand, this dimer could be a ferromagnet, or it could be an antiferromagnet. And of course, because of the fact that you could get both a ferromagnet and antiferromagnetic behavior, it's of a lot of interest. The other thing is that just like a lot of other single molecule magnets, these could also be crystallized from where we've got all the parameters, in other words, the coordinates of these atoms that make up this molecule. And it has strong intramolecular interaction and weak intermolecular interaction. And of course, we are hopeful that it also has a slow relaxation. Just to, this cartoon over here shows you the antiferromagnet, and here you have the ferromagnet. You have the size of the system here. It's about almost 2 nanometers and by 1.5 nanometers. And the question that Zahra was asking in this talk was that how would the substrate affect the magnetic properties of these manganese 3 dimers? What we know here is that the spin is 6. This comes from experimental values, and I'll talk about it some more in the next talk. How are these going to be affected by the substrates that we use? And the reason that we want to think in terms of substrates is that we are obviously interested in interrogating these dimers, and the only way to do that, if you want to have a spin transistor or for any kind of applications that you want to do, single molecule transistors and so on, you have to have something on which they can be stabilized. And so what we will be looking at here would be on 2 surfaces. We would be looking at it on graphene and on hexagonal boron nitride. These are again two materials that have recently been studied for a good number of reasons. And we want to see what the effect would be when these molecules are deposited on these surfaces. This, by the way, is also because Art Hayward, in our collaboration at University of Florida, is setting out to do measurements on this system. And this is also work with Xiaohong Zhang, who's also listening to this presentation, that we will be doing with him. So for the part here, we certainly realize that DFT is not always the best way for magnetic systems, but it seems to work actually reasonably well. We do apply DFT plus U, and perhaps we'll apply even more advanced methods. But for the purposes here, these calculations were carried on with using DFT in the usual way that it is done. We did have, just to make sure that there's no interaction between the molecules and their images, because DFT, when you do these calculations, they are it's based on a supercell, and the supercell actually has to be pretty large. If these are very large molecules anyway, but also you don't want molecules to be interacting with their images. So it's a lot of large vacuum that Zara had to take to get really converged results. Converge meaning that there's no effect of the supercell on the proper quantities that we calculate. So what we are showing you here, we'll look at the absorption configuration and energies. And so again, you've got these here. You're looking at, on the left, you're looking at the ferromagnet. And we tried several configurations. We're showing 3 of them here. The 3 that, so with about a dozen configurations were tried, not infinite. And of the dozen, there were 3 that showed that you have a good binding to the surface. Of course, these are bound, as you'll see, by van der Waals forces. So this is not, you know, a chemisorb system. It's a physisorb system. And what you find here is that the binding energy per molecule is something of the order of 1.5 eV, between 1 and 1.5 eV. What it does do, here you're looking at graphene, is that you do get a corrugation on the surface, which is interesting. This is, again, the molecule is sitting, as you see here, about 2.5 angstroms away from the surface with van der Waals interactions, but there is a corrugation that is introduced. The other thing that is also interesting to point out is that there is a change in the size of the molecule. The molecule actually, to my surprise, it actually liked to sit, particularly in the ferromagnetic case, more or less straight on the surface. So essentially, the hydrogens and the carbon atoms from the molecule, from the ligand, wanted to coordinate with graphene. And so the manganese is actually a little bit further away, removed from the surface here. And the molecule itself goes shrinking when it is in the antiferromagnet, in the ferromagnetic phase. And actually, there's a little bit of breathing when it is in the antiferromagnet. In the antiferromagnet, actually, it is much more symmetrical here and not trying to stand straight up, as is the case in the ferromagnet. So the preferred orientation, so if you're just about to look here, so this is the preferred orientation for the ferromagnet, and the one in the middle. And again, this has to do with, so what Zehra and Renier did is that they looked at the orientation of the manganese atom with respect to the graphene underneath. So they were looking at the various, you know, the molecule itself has C3V symmetry, and the symmetry of the surface itself, it's a hexagonal surface. So they looked at adsorption positions that dictated by their symmetry. So they tried the ones with different symmetries. And so it could be, for example, on the hollow site, or it could be on top of one of the carbon atoms, and so on. And that was what led to these various choices over here. Of course, because it is physisorbed, you know, it could be on a number of places on the surface. There's no chemical bond that is formed in the 2 cases. What is interesting when you do the charge analysis is that even though there is no chemical bond formed, you actually do get a lot of a charge rearrangement. So this is the charge rearrangement that is being shown in the case of graphene, the molecule on graphene. And so what you find here is that this one, actually much more of the rearrangement is for the atoms that are very close to the surface. And and it is more in the case of the ferromagnet than in the case of the antiferromagnet. And so when the next is to look at these magnetization here. And so, and I'll talk about it a little bit more when I talk about the single molecule. I'm showing you the results here only for the uncharged dimer. We have results also for the dimer when it has a charge. And in that case, this value will become 24, which will correspond to a spin of 12, which is what they see in experiments. But for the case over here, what we wanted to point out to is in the case when you have graphene, there is a little bit, there's a little bit of a change in the magnetization. It's very small, but there is some. And certainly you see some in the case of the antiferromagnet. Again, very interesting observations here. So the next is that we look at another molecule here, and this is another support, which is the insulator. This is the hexagonal boron nitride. And what we find over here, I have a feeling my time is coming to an end, so let me walk you through this. So if you, you may not remember this, but the energies were very similar. I had said that the energies were between 1 and about, say, 0.5 to about 1.5 eV. Very similar energies for adsorption over here. Again, these are the three sites that we show here, very similar to the case when you had them on top of graphene. The one thing to point out is that there is actually, okay, okay, I guess my time may be coming to an end. I see some messages. This here is basically the shrinkage that has gone on. So about half an angstrom of shrinkage of this molecule, and a little bit of a breathing in the case of the antiferromagnet. And so the other thing is also that the corrugation is actually larger in the case when it is on hexagonal boron nitride, which is kind of understandable because unlike graphene, you have boron and nitrogen over here. So there is some tendency for these strain effects to be even more important here. Let me see. So these are then the positions where they like to be adsorbed. Let me then move on again to the charge analysis for the case of hexagonal boron nitride. And once again, what we find is that there is, and in this case in particular, you're seeing this is showing you how the electrostatic potential between the molecule and the surface is changing. You know, there are no chemical bonds here. This is just rearrangement of charges that is going on. And as you can see in this case, the manganese and the oxygen and nitrogen atoms around it, they really are not affected that much, and the effect is mainly at the interface. The effect in the case of the antiferromagnet is even smaller. So the charge transfer, as you will imagine, because we're looking at this insulator here, is very, very small. In the case of graphene, I don't know if I pointed out to you, the charge transfer was about 1 electron, 1.26 electrons here, and about 0.3 or so electrons in this case. So there is charge transfer in the case of graphene, but hardly any in the case of hexagonal boron nitride. So again, this is my summary here of just what happens to the magnetization. And I should just say that not much happens in terms of the magnetization. And that brings me to the last slide, which basically says that both of these, we investigated the effect of the substrate. In both of these, they do adsorb and seem to be stable on the surface. The boron nitride actually affects the molecules much less than graphene, but even graphene does not distort the magnetic properties too much. So thank you.
Thank you. We don't have time for questions on this talk, but Talat is the next speaker. So